right, everyone. So we are going to have 4 short talks, which are 5-minute long, and so we don't have time for questions. So I encourage you to meet with the speaker if you have questions during the break. So the first of these talks is going to be by Mohamed Djekidel from Tsinghua University, and he'll be talking about find differential interactions.
So good evening, everybody. So today I will add to the presentations of the morning and present another differential chromatin interaction detection method called find. We know that with the availability of the high-C data make it of interest to do more comparative analysis. However, when we go through the literature, we notice that there is no explicit method to detect the differential chromatin interactions. And generally, researchers use some count-based methods, such as the fold change, or adaptive methods, such as EdgeR. But at a high resolution, the problem with these methods is that they treat each pairwise interaction independently. But we know from the polymer physics simulation and from the exclusion model that a change in the interaction frequency between two loci has an influence on the neighboring interactions. And this dependency between the neighboring loci can be checked using what we call the directional variogram, which is a function that measures the variability between points separated by a distance h. And for example, here in chromosome 22, we can see that if we move further from any given point to any direction, well, we get more variability. So given this observation, we first built a model, and then we did some simulation to validate it, and then we checked it on some real data. And the basic idea of our model is that if we look at high-C in the 3D space, we can imagine a differential chromatin interaction as a change in the interaction intensity in the point and in its neighborhood. We can formulate this as follows. So given that we have 2 experiments, condition 1 and condition 2, each having a different number of replicates. And suppose we are interested in checking the interaction, the differential state of interaction Ig. So we define a window around the interaction Ig, and the idea is that if you have a differential interaction, a true differential interaction, you should see a lot of the neighbors, they also show a difference in their interaction frequency. In other words, we can say that if we suppose that if we take the mean of the interaction Ig, for example, it's mu1, and we order the points in this window according to their distance to mu1, we expect the k nearest neighbor from condition 1 to be, if there is no differential interaction, we expect them to be located in the same, almost like in the same, have the same density around mu1 as the k nearest neighbor from condition 2. And basically, for a window of w multiplied by w, we get about w square k nearest neighbor. And we get for each k nearest neighbor a p-value, and we aggregate these p-values. And mathematically, using a spatial Poisson process, which I don't show all the details here, we can show that the change in the intensity between condition 1 and condition 2 for a fixed k follow a Fisher distribution. And as it was presented in the tree high-C, we had a problem in fixing the FDR. And well, the best what we could do is we take all the p-values using mu1 and mu2 as references. We get about 2 w square p-value for each interaction. We aggregate them using the ROP statistic. We get p-value. And then to avoid having, to control for the false discovery rate, we apply what we call a quantile regression that tries to detect the best p-value for each interaction distance. And then we took this model, we compared it with EdgeR. And here in this graph, find is shown in blue and EdgeR shown in red. And we compare the performance of our method given different fold change, given different window size, and also the percentage of the percent of differential k nearest neighbors. And we can see for a window size less than 5, which is about 25 KB, our method performs better than EdgeR. However, for a larger window size, our method performs very poorly because we lose the independence condition. However, for a high fold change, our method show similar, or EdgeR show similar performance as our method. However, even in similar performance condition, if we check the false positives of EdgeR and ours shown here in green, we can see that EdgeR false positive tend to be located randomly in the heat map. However, our false positive tend to be located next to the true signal shown here in blue and orange. We also compared between K562 and JM12878, and we show that we can find more differential interactions, and they show a smaller span compared to EdgeR, and the majority of them are located into TADs, and they are associated with differentially expressed gene. Because speed is an issue, so we tried to improve that. We used RCPP IGen. We combined that with the sparse matrix representation and in-memory processing of the data, and tried to add some parallelism. And our package is available here. And so basically, I think I arrived to my time. I want to thank my supervisor. I've already graduated, Professor Michael Jha, and his assistant, Professor Chinia. And thank you very much.